I'm Anil Kumar. Now, let us review whatever we have learned about dot products. So, in this particular video, I'm going to share with you many topics. We'll understand what are multiples and products in vectors. We'll find angle between the vectors. We'll do some basic calculations to get started with dot products. And then take up test practice questions. Now, that part is huge. So I may run into part 1, 2, and 3 to discuss them all. The type of practice questions which I have taken are as follows. So like here, we have a multiple choice question. You can always pause the video, copy the question, and then try solve them. We'll get back to these questions soon. Then we could have a question like this, where we are talking about sum of two vectors. We need to find angle between them using dot product, of course. And we have the same thing. We know the sum as given earlier and how to find dot product of a combination of vectors as given here. And then we'll look into parallel and perpendicular vector examples with unit vector calculation also. So we have huge application of dot products as projection of vectors. So we'll consider the basic concept questions as given here, and then we have a very interesting question on vector projection, where we'll understand the projection geometrically and also calculate the values algebraically. Based on this, we have a bonus question where we'll try to find area of a scalene triangle using only dot products. Remember, cross product cannot be done or cannot be applied for R2, right? That's valid for R3. And then we'll have an application question based on work done. This is where we started. So let's get back to our questions. We have one more here, which is just a true or false to summarize all what we have learned, right? So these are all the topics. Now let's begin from the very first page, basic understanding of dot products. So let's figure out what we have learned about multiples and products doing vectors. Multiples, you have done scalar multiple, right? So this term is very familiar with you, scalar multiple. It really means that if I'm given a vector, let's say that's the vector given to us. Let's call this as vector u. In that case, if I want to find what is half of u, now this number half is scalar, right? So if I multiply, we get a vector which is just half the length. So the magnitude actually becomes half the magnitude of the vector. Direction remains same. So this vector becomes half u, right? So that's the vector half u for us. You could also have negative constants to multiply with. For example, we could have what is minus u, right? So that means that we are actually just reversing the direction. Instead of going towards northeast kind of thing, it may be like this, correct? So that becomes minus u. So these are scalar multiples. So they actually change the size or the magnitude of the vector, direction remaining the same. Well, it could be reversed as you have seen with negative numbers, right? In physics, we come across a very interesting thing. That is to say, when we apply a force on any object and it moves. For example, let us say we have a ramp here. Let's say we have a ramp here. Now, if I want to move an object up the ramp, let's say this is the object, and if you want to move it by applying some force, and let us say force is being applied in a direction which is at an angle, not exactly the same thing, but let's say the force applied is in this direction, let's say, right? That's the force we're talking about. In that case, what is the work done in moving the object from this position to let us say this position. Let's call this as the distance of d along this slope. So what we figured out is that if the angle is theta in between them, then the work done W is really equal to magnitude of force applied times the distance moved times cosine of the angle theta, that angle. Right? Same force being applied to move an object along a ramp gives you something like this as the work done, right? So Newton meter could be the unit, or joules could be the unit. On the other hand, we also saw an example which is, let's say here is a wrench, right? So let's say this is a wrench, and we are applying a force on this wrench. So let's say the force applied is kind of, we want to move it like this, correct? So the force applied is right here. Now, what really happens is that, and let me show this force, it looks like a right angle. Let's say the force applied is kind of here, okay? So let's say that's the force being applied. Now, truly speaking, what we notice here is that if the distance from the point where effective force is being applied, if I move in this direction, that is, let's say there's a nut bolt here, it goes down, right? This is given by the right hand rule. Let me write down. Right hand thumb rule. And if this distance is, let us say, r, then the torque is magnitude of force times magnitude of r times sine theta. So whereas in the work done it was cosine theta, here it was sine theta. The idea was that the force, sine theta is this component, which is, let's say, let me now drop a perpendicular from here. Right, so if that is the, or let me show it like this. Let's extend this a bit. So if I say that theta is this angle, right, then from these parallel lines, theta will be that angle, and this component here is f sine theta. Right, so this is what you learn in physics. How do you explain that in vectors? Now these two seemingly similar things, force being applied for a distance or at a distance, but with very interesting different results, gave rise to two kinds of products in vectors. The product which gives you just a quantity here, force magnitude, distance magnitude, angle, the number itself, results into a scalar quantity, right? Now to explain this, we have dot product, which we are going to work out in details. And we say work done is force dot displacement, right? Let me not say distance, displacement now, just to make it a vector. Displacement gives you magnitude and direction. And this is calculated as magnitude of force times magnitude of displacement times cos of theta, the angle between them when you could put tail to tail, right? Here, that quantity is actually represented by cross product, which is vector. Vector in the sense that gives you direction, right? Direction by the right hand thumb's rule. So if I move it in this direction, it will go down, right? So that's the whole idea. So we say that the torque is the cross product between the vector force and the displacement, I should say, the radius of this r, right? And the direction of this vector will be given by the right hand rule. So as you can see here, dot product basically gives you work done kind of a thing, and the cross product gives you the torque kind of a thing, right? So cross product is a vector quantity, results into vector quantity. Dot product results into a scalar quantity. It is also sometimes called scalar product for that reason. So that's very important to understand. Now, one more concept, angle between the vectors. Let's try to understand that also. If I am given these two vectors, let's say this is one vector, the other vector is, let's say kind of like this, making an angle phi between the two. Let's call these vectors as A and B. This is vector A, this is vector B. In that case, what is dot product of A and B? Well, it is magnitude of A times magnitude of B times cos of an angle. Well, which is that angle? Is it phi? No. The angle here is the angle when we place them either tail to tail or head to head. Now this is very important to understand. When I say tail to tail, that means this is a vector, right, which has got that much of magnitude. I could consider this vector like this. It's the same vector A. Is the same vector A, right? Now this angle, the angle when they place tail to tail will be called theta, right? So that is the one which comes in your formula, right? Or you could have placed them head to head. That is to say, well, this was vector A, B vector considered like this. Now both heads are here, perfect. So the angle, this angle will be angle theta. So they are right. Vertically opposite angles always equal. So that's the angle which you have to always consider. Perfect. Now, since you know that A dot B is magnitudes times cosine of theta, now theta could be equals to 90 degrees. In this case, they are perpendicular vectors. It's kind of like this, right? It's kind of like this. So in this particular case, when theta is 90 degrees, and let's say the vectors are P and Q, then P dot Q will be equal to 0. So we say these vectors are orthogonal. Okay. Now, you could have vectors dot product as negative or positive. For example, if I have a vector like this and the other one is opposing it, right? So the other one is opposing it as we showed here, right? What I'm trying to say here is, let's consider these two situations. Now here I have another vector which is helping it. So kind of like this. Do you see that? It helps to move it in that direction. Angle between them will be this angle theta, and you can see that angle theta is greater than 0 and less than 90 degrees. So in this case, if I have vector u and v, then u dot v is going to be positive. Is it okay? However, if I have a vector which is opposing, in that case, what is the angle? Well, the angle now is, let's say theta again, and let's call these vector as S and T, right? S and T. Then the dot product of S and T is going to be negative since the angle theta is greater than 90 degrees and less than 180 degrees. Do you get the idea? Right? So the dot product could be positive or negative. Well, if dot product is negative, we do not say it has a direction. Okay, it is just opposing the movement if you consider displacement. Think like that, right? This is like a wall, right? Here it is helping it to move in the same direction is positive. So that could help you to understand when a dot product is positive and when it is negative. Now since we know that it results into 0, when the two are orthogonal. In that case, if I have, let's say, dot product of A and A vector by itself, then what happens? Well, if I take this example, vector A dot A, the angle between them is 0. If the dot product is not 0, it means magnitude of A times magnitude of A times cos of 0. Cos of 0 degrees is 1. So what we get here is magnitude of A square. So dot product can also give you magnitude of a vector itself, right? So square of the vector. So that's an idea. How do you find the magnitude of a vector, right? So that's the way to find magnitude of a vector. Now, simple calculations to find dot product is, if I have, let's say, 1, 2, 3 dot, well, I've taken this as a position vector, okay? Let's say minus 1, 1, 0, let's say. We are taking very simple calculations. Then, since these are components in I, j, k direction, 1 gets multiplied by minus 1, resulting into minus 1. 2 gets multiplied with 1, so you get plus 2. 3 times 0 is 0. When you add them up, you get 1. So that is the scalar quantity dot product of these two vectors. So that's a very simple way to find dot product. If they are given in such a way, or let's say, if you have to find dot product of 2i minus 3j plus k times, let's say, I minus j plus 2k, for example, then the idea is you just multiply their I components, j components, k components, and add them up. So what do we get here? 2 times 1 is 2, minus 3 times minus 1 is plus 3, 1 times 2 is plus 2, and what you get is 7. So that is how you could calculate the dot product. So I hope with this you have a fairly good idea of what dot product is, and with respect to multiples and cross product, you have an idea where we are. How to find angle between these vectors? You should place them tail to tail or head to head. And we have done some basic calculations to find dot product, including the fact that you could use dot product to find magnitude of the vector by having dot product by itself. And now, with that knowledge, let's move ahead and take up some test questions, right? So these test questions are actually selected ones. You'll find them very interesting and useful. Feel free to share your views and comments, and if you like and subscribe, that'll be great. Thanks a lot for watching. Now here is your first test question. Now we'll talk about many concepts relating to dot product with the help of this particular test question. We are given A, B, and C are three non-zero vectors such that A dot B is equal to A dot C. Which of the following is always true? Four options are: magnitude of B is same as magnitude of C, B is perpendicular to C, A is perpendicular to B minus C, or A equals to B minus C. These are your four options, correct? To help you answer this question, we have question number 2. It says explain why the option A is incorrect. I've seen most of the students answering the very first one, that if A dot B equals to A dot C, then the magnitude of B and C are equal, which is absolutely incorrect. So give you a hint. Question number 2 is explain why option A is incorrect. And question number 3 is what else can be true? So of course, one of these options true, but what else could be true about A dot B equals to A dot C? So that makes it very interesting, and that will help us to understand dot products better and move on to take few challenging questions on dot product. Okay, so let's look into this. A dot B equals to A dot C. Sometimes we represent vectors as bold letters. When we write, we can't make them bold, so this means a vector. I may miss at times to put that, but just treat them as vectors as I speak. Okay. Now we can rearrange them, bringing A dot B minus A dot C equals to 0. Now dot product they do follow distributive property, as you know. So we can write this as A dot B minus C equals to 0. Now that is 0 if A is 0, but A is non-zero, it cannot be, or B minus C is 0, correct? Or B minus C is 0. But we are not given that option here. The option which we are given here is A is perpendicular to B minus C. Does that make sense? So when we have a dot product equals to 0, that means we are looking at an angle of 90 degrees, right? So that really results into that this is possible when vector A is perpendicular to B minus C, correct? So that gives you the result. Okay, now tell me why option A is incorrect. Magnitudes of B and C. Why is that incorrect? So let's look into that part also. So at times, dot product, we write A dot B as equals to magnitude of A times magnitude of B times, let's say, cos of alpha, where alpha is the angle between A and B. Now if I say A dot C, it will be magnitude of A times magnitude of C, okay, times, let's say, cos of beta, where beta is the angle between A and C. Do you see that? So if you say that A dot B is equals to A dot C, it really means that A and A is common. That really means that the magnitude of B cos of alpha is equals to magnitude of C cos of beta, right? So that becomes another condition which is always true when their dot products like this are same. So we could add what else can be true. So what else could be true was that magnitude of B cos of alpha is equals to magnitude of C cos of beta. Do you understand? So their projection kind of thing on A is same, correct? So which is also, so we can say if their projection of B is equal to projection of C on A, right? So I should have written projection of B on A, right? So I should have written projection of B on A is equal to projection of C on A. If they are projections, these are the projections of these vectors on A. If they are equal, then the dot products will be equal, correct? Now this criteria also gives you an option, right? That is to say that vector B is equal to vector C, right? So there are a couple of options which you could have given. So I hope you find this question very interesting and useful to understand dot product. So these are the two ways, you could do dot product and understand the concept, correct? So let's move on to the next question now. I hope you find it interesting. Now I'll take two related questions. Question here is based on, for unit vectors A and B, magnitude of A plus B is square root 5 over 2. So based on this, we have two questions. The first one is determine angle between the two vectors, that is, find the angle between A and B. And the second one here is determine the value of 3A minus B dot A plus B, right? So what I will do here is I'll actually find the dot product without calculating the angle. So, and we'll do the first part later, right? This is only to show you that necessarily you do not have to find the angle to get the dot product. I hope you get the idea, right? So what we are trying to show here is that we may not find the angle to get this result, okay? But if both the questions are given to you, then it is a good idea to find the angle, right? Okay, so let's work on this part and then we'll get to the second part. Since, as I said, you don't really have to find the angle between A and B to calculate the dot product. Let's see how. So we are given here 3A minus B. A and B are vectors. Dot product is always between vectors, right? Okay. Now, so that really means I could write this as equal to. So 3 times magnitude of A squared. And I forgot to write here that both are unit vectors, right? A and B are unit vectors. Correct. So let's move on. And then we do 3 times, that is plus 3 times A dot B. And then we have minus A dot B. Okay. And then we have magnitude of B square with a negative sign. So that is their dot product. And of course you do have a term which is A dot B, which was easy to find if you knew the angle. We will try to see how to figure it out without knowing the angle between them. So let me write this as magnitude of A plus 2 times A dot B minus magnitude of B whole square. Okay. Now, if you are given the magnitude of a vector, which is A plus B, then you could actually, here we are given square root of 5 over 2, correct? So if I square both sides, what do I get? I get A plus B whole square equals to 5 over 2. Does that give you an idea? So the idea here is that what is this A dot B whole square? Basically, it is A plus B dot A plus B, right? So when you do dot product by itself, you get magnitude square. That is what it is, right? So this is equal to 5 over 2. Now if you open this up, you get magnitude of A square plus A dot B. Okay, so A dot B plus B dot A plus magnitude of B square equals to 5 over 2. Now here do you see that term 2AB? So we have magnitude of A square plus twice A dot B plus magnitude of B square equals to 5 over 2. You get an idea. Now we know that this magnitude of A square, B square is 1 since they are unit vectors. That means magnitude of A equals to magnitude of B, which is 1, correct? So I could always replace this at 1 and get what 2A dot B is. Perfect. So from here, I can write 2A dot B is equals to, this is 1 plus 1 as 2. So 5 over 2 minus 2, which is 5 minus 4 over 2, and which is half. Do you see that? So 2AB is half for us. So therefore, I can write this as, so we'll substitute this half here now. You get an idea, right? So this is twice AB is half, correct? So now it is simple. We could, we could do it anywhere. So this is 3 times 1, right? And that is minus 1. So what we get here is 3 plus twice AB is half. minus 1. That is what we get, which is 2 plus half, which is 4 plus 1 over 2, or just 5 over 2. Does it make sense to you? So we could actually figure this out without finding the angle, and this is a simple process. I was trying to explain you, so it took longer. But anyway, for any vectors a and b, we could do this, right? Okay, so now let's find the angle between the two vectors. Okay, so let's get back to our question, which is we are given vectors a and b. Magnitude of their sum is square root 5 over 2. We need to find angle between the two vectors. So let me sketch to understand the scenario. So let's say this is vector A, whose length is 1 unit, right? And since we are given their sum, I'll place vector B kind of like this. Okay, so the length is 1 unit. Now, what we can do here is that we can find the resultant, which is the sum. So that becomes the sum, correct? So now, if I have a vector A and vector B, then this becomes vector A plus B, right? Now we can use the cosine law to find or relate these. So this resultant is actually related with this angle, and let's call this angle as phi, correct? Remember, the angle between the two vectors is not phi. The angle between the two vectors is this angle. We call this as theta. When you place them either tail to tail or head to head. So if you place them tail to tail, the angle is theta. That's a very important thing to understand, right? Okay. Now, from here, using the cosine law, which is, we can write down that the magnitude of this a plus b whole square is equal to a square plus b square minus twice ab cos of angle between them, which is phi. You get an idea, correct? So that is what relates them. Now a plus b whole square is 5 over 2 square root, and we have to square it. Perfect. Magnitude is 1, so we say 1 plus 1 minus 2 cos phi. Correct? Now this is 5 over 2, which is equals to 2 minus 2 cos phi. Now to bring it, we can say 2 cos phi is equal to 2 minus 5 over 2, or we can say 4 minus 5 over 2, which is minus 1 over 2. Perfect. So cos phi is equal to minus 1 over 4, right? So cos phi is minus 1 over 4. Now what is cos theta? Now if you want to write this phi in terms of theta, we have to find angle between the two vectors, which is theta, right? So theta is actually equals to 180 degrees minus phi. Do you see that? So I could write this as, we can write this as cos of 180 degrees minus theta is equals to minus 1 over 4. Perfect. Okay, so let's get back to this place. So that tells us cos of 180 degrees minus theta is actually minus cos theta, since you are in quadrant 2, right? So let me review this. So we are talking about the angle, which is as relating to kind of theta. 180 minus theta is basically this angle. Is it okay? Where this is theta, right? This is 180 minus theta. Now since you know cos is negative, cos is positive in quadrant 4, not here. So we know this part should be written as cos of theta is equals to 1 over 4. Do you see that? So what we get here is cos of theta equals to 1 over 4. perfect. So theta is cos inverse of 1 over 4, right? We can use calculator to find this out now. So we have shift cos inverse and 1 divided by 4, bracket close, equals to. So we get 75.52 degrees, right? So that is how you can actually find the value of theta, right? Now if we combine this example with the dot product example, then you could use the concept that A dot B is equals to magnitude of A times magnitude of B times cos of theta, right? So you don't even have to find the angle. 1 over 4 will work, correct? So in this case, it will be 1 over 4. You get an idea. And that value could be used in the example which we had, right? So where we used the dot product concepts to figure it out. So I hope that makes a good connection, correct? So at times you may find all this and then do the second part, or if this is not given to you, you can go direct as we did. But I hope it helps you to understand dot products better. So now let's take more examples from our test papers on dot product. Now here is another test question on application of dot products. We'll relate parallel and perpendicular vectors. We are given vector v as 3, 2, minus 1 and vector w as ab2. Two parts of this question are determine w if they are parallel, and b is determine unit vector perpendicular to v, right? So these are two very important questions. So let's do the first part, which is we need to find w if they are parallel. So we are saying that vector v is parallel to vector w. That means what? We are actually looking into scalar multiple, right? Not dot product. So that really means that vector v times something, since this is 2, this is 1. So if we could say that k times v is equals to the vector w, then they are parallel, right? So they are scalar multiples. Now in this particular case, if I write k times vector v is 3, 2, minus 1 and vector w is a, b and 2, I could see very clearly that this is minus 1, that is 2. So that gives me k equals to minus 2, correct? So using the value of k as minus 2, let's write minus 2 times 3, 2, minus 1. We could get this vector as minus 6, minus 4, plus 2. You get an idea. So for the vectors being parallel, we can say w equals to minus 6, minus 4, 2, which is parallel to the vector v, correct? So that is how you get part A. So part A basically is an application of scalar multiple. Now part B, unit vector perpendicular to v. Now when we talk about perpendicular vectors, that means using w, let's use w itself. That means the dot product is 0. That means dot product is 0. So let's find dot product. So we have 3, 2, minus 1, dot product with a, b and 2. We have to equate this to 0, right? So that means 3a plus 2b minus 2 equals to 0. And that gives us 3a plus 2b equals to 2. Now that is a linear equation with two unknowns, a and b. So that means we have multiple solutions, right? So we have multiple solutions. So the idea here is that you could give different values of a and b and then calculate, correct? That's the whole idea. So if I say that, just to keep them whole numbers, so if I say b is 3, for example, right? So if I say b equals to 3, then we have 3a plus 2 times 3 equals to 2. Or we have 3a equals to 2 minus 6, which is 2 minus 6 is minus 4. I don't want to work with fractions. So let me take a as 2, right? So let's take a as 2. So let me not take this value since it gives me fractions. So what I will do here is redo it with a equals to 2. Let's say, okay. In that case, this is 6 plus 2b equals to 2, or it gives me 2b equals to 2 minus 6, which is minus 4. So b is minus 4 divided by 2. So b is minus 2. Is that okay? So we'll go work with this value. Okay, I still have some space to work with. The idea is to get unit vector, right? So, okay. So we do have w, which is now, since we take a as 2, b as minus 2, perfect. And already we had 2 here. Good. Now definitely this vector is not a unit vector. Since we need a unit vector, how do we figure that out? So the unit vector will be, let's say the unit vector normally written like this, will be the vector itself, the vector itself divided by its magnitude. So the magnitude of this will be, let's write down, over square root of 2 square minus 2 square and this 2 square. So let me write down here 4 plus 4 plus 4, right? Which is square root of 12. 12 is 4 times 3. So I could write this as 2 minus 2 divided by 4 square root 3, which is 2 square root 3, correct? So that becomes a unit vector. So let me just push this page a bit. And yeah, so the unit vector will be, so you could actually divide them by 2. This is a position vector. So you could write this as dividing with 1 over square root 3. Do you see that? And this one is minus 1 over square root 3. And the third one is again 1 over square root 3. So that becomes the unit vector, which will be perpendicular to the given vector, right? So let me rewrite here. So unit vector W will be 1 over square root 3 minus 1 over square root 3, 1 over square root 3. Okay, so that is how you can find unit vector perpendicular to given vector using dot products. So with this, I hope you understand many concepts about dot product, and with this practice of test questions, you should be good to go with the rest of the questions. So we'll end our part 1 on review of dot products here. The rest of the questions we'll take up in part 2. Thanks for watching. Feel free to write your comments, share your views, and if you like and subscribe, that'll be even better. Thank you and all the best.